Let's begin. Last time we talked about, hey, what's going to happen to a hole if you heat it up? Will the hole get bigger, smaller, or stay the same? And we all tried it with our kid sister's ring, and we found out what, gang?
Smaller.
See, right now, it goes through. With a little effort, it goes through, yeah? I'm not going to take the time to heat up the ball. I'd waste your time, because you know the ball would get bigger and no way it would go through. I'm going to heat instead the ring. You get that ring nice and hot. Is the ring expanding? Yeah, it's expanding. How about the hole? Is the hole expanding? See, a lot of people think this. A lot of people reason that the hole is it's going to expand this way and expand in this way because the ring is going to get fatter. Will that ring get fatter? Turns out it will. So they think this part will expand out here, and this part in here, and the hole gets smaller. But lo and behold, it's appreciably bigger. So the hole does get bigger again. Did that kind of confirm your reasoning anyway? Did you find it? How many people said in their homework, yeah, the hole does get bigger? Show of hands. How many people are a little bit unhappy today? They kind of said something else. Can we still be friends? Can we? Here's a way to look at that, gang. No friends today? Uh-oh. Sometimes it's not good to give the answers, huh? If we take our ring and we cut it up into 4 pieces, gang. 4 pieces. And if I put any one of those pieces in the oven, would it get bigger? Yeah. Would it expand and maybe look like this? No way! It's going to expand and look like that. And this side here is longer in an expanded state than like this. So take them apart and look at it and you can kind of see it. Or take your ring and open it up like this. Is it going to get fatter? Yes, it's going to get fatter. So it expands out to here maybe. Out to here maybe, yeah? But that's not the end of the story. You see, we're so busy thinking about what happens like this, huh? That we forget it's expanding this way too. And it expands lengthwise as well. And lengthwise, we see it expands out to here. And I submit to you that this dotted line on the top is longer than this solid line below. And that dotted line on the top represents the new inner circumference. So every part of the ring, the thickness, the width, circumference, outer, inner, everything expands by the same rate if the heating is uniform. And it pretty well was here. So the hole gets larger. Okay? You've got a jar of peanut butter, you can't open it up. You give it to a muscle-bound type, still can't open it up. So what do? And I hand it to you. You take it over, put it in the stove upside down momentarily, or put it under the hot water. Doesn't that metal lid expand? Does that make it tighter against the glass or looser? Looser. And they're, hey, mind. Hey, bronze one thing, wonderful, but the mind too. See? So you think, and you can open it up by just heating it up. Turns out the whole darn thing will expand, whole and all. Neato? Sure, another kind of nice thing too. You have thermostats at home? Here's a piece of metal. 2 kinds. Brass, steel. Does everything expand the same rate, gang? Let's see. Steel's on the top, the brass is on the bottom. Which part expanded more? The brass. The brass expanded more and pushed the steel right into a curve. You see that? And that's the basis of a thermostat. Thermostat acts like that. You know what I'm saying? Okay. Notice we have a wooden handle on here. Why do we have a wooden handle on this demonstration apparatus? Here's metal here. I can just barely hold it there. Why is it I just didn't have the metal and hold that in there? Why, gang? Because the metal part would get hot, and the wooden part wouldn't. And that wooden part wouldn't. But why, and what are we going to talk about today? Heat transfer. And the first kind of heat transfer begin with a C, and what is it? Conduction. And it turns out that heat would have been conducted to my hand had I held it here, and it would have burned me. That's because metal is a very good conductor of heat. How come I got a wooden handle, gang? Because the wood is a very poor conductor of heat. But let's not be so negative. Instead of saying poor conductor, we can say good insulator. See? See the other way around? Okay. It turns out in a metal, all metals, got loose electrons. And those electrons, when you start to heat this up, how many people say, oh, when you put that in the flame, those electrons just kind of hang loose on it? Those electrons are bopping around. And those electrons, bam, 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 hit their neighbors, and that energy cascades all down the metal. So it turns out that things with loose electrons are good heat conductors. Later on, we're going to learn things with loose electrons are good electrical conductors. And how many say, oh, that's probably a coincidence? It's not a coincidence. It's a good electrical conductor for the same reason. Those loose electrons can flow right through a piece of metal, gang. And when we're talking about electricity, we'll be talking about that soon, yeah? But for now, those little electrons will bop, 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 which are loose in metals, and carry that energy right along. So some things conduct better than other things. Piece of wood, very, very good insulator. This wood's a good insulator at any temperature. This wood is a good insulator even if it's very, very hot. Yep. Did you ever reach into a hot oven and grab onto a frying pan that's about maybe 400 degrees Fahrenheit? You want to cook some food or something, you got a frying pan in there and it's all iron? Ever be reaching in with your bare hand and grab the iron pan? If you ever have, you can show that today. You'd be tattooed, right? You're going to burn yourself. Isn't that right? But could you reach into that oven and grab a pan if it had a wooden handle and grab it momentarily? You can do that. You can do that. You know why? Because that wood is hot. It has the same temperature as the metal. But not very much energy is going to conduct from the wood to your hand. So you can safely hold it. You can do that. You ever see these people walking on hot coals after they've paid more than $300 for some sort of a course that teaches you how to have self-confidence in yourself? And then the test of that self-confidence is they say, we are going to violate the laws of physics and show you that mind over matter, that $300 you've spent for that 15-minute session is going to pay off because we're going to apply those techniques and we're going to show that you can walk with bare feet on hot coals. And so the people do that. They take off their shoes, bare feet, they step on the hot coals, they walk across, and they think they have violated physics. Gang, those are hot coals of what? Wood. Wood. And that wood is very hot, isn't it? How much of that heat in that wood is going to get to the feet? What does it depend upon? Not only the temperature of the wood, but something else. Begin with a C, end with conductivity. See if you can put it together. What is it, gang? The conductivity. And the conductivity of the wood is good or not so good? Not so good. So when you step with your bare foot on that hot coal, there's a heat transfer. A lot or a little? What's the answer begin with, gang? Okay, L. Okay, so it's a little L, right? And so that's really, really neat. Only a little bit of heat will get to your foot. And you can walk. Now, you're not going to stand in one place there, okay? You're not going to reach in that oven and just hang on to that wooden handle. And you're going to be hurt. But you can grab it and pull it out, boom. And you can step across red-hot coals of wood without harm. It's even better if your feet are wet. Remember you're a little kid and you wanted to know if the iron was hot? And your mother says, touch it and see. Now, if your mother doesn't care very much for you, she says, touch it and see. But if your mother really loves you, she says, before you touch it, be wet in your hand. Psst, right? Psst. That little sound? Psst. What's that little sound? We're getting a chapter ahead. You guys don't know about this. It turns to steam. How many say, oh, don't take any energy to turn to steam. It just happens to do it. Come on. The energy it took to turn that to that little puff of steam is energy that did not go to your hand. So it's better if you walk across those coals and you got wet feet, because then it'll be even safer. So a homework assignment this weekend. Everyone take off their shoes and socks, get some hot coals, pour them all over your front lawn, and get out there and do it. All right? Okay? Extra. Some people say, anything I can do for extra credit? There you are. And take a photograph of it. And we'll put the photo in the next book, okay? Because I need to get a new photo of someone doing that. All right? You're sitting at tables. Part of your table is metal and part of your table is wood. I want you to all put your hand on the wooden part. Oh, go ahead. It's all right. All right. Now take the hand off and touch the metal part underneath, the metal part of your table. Okay? Now, which is hotter, the wood part or the metal part? Well, that is kind of an ambiguous question, gang, is it not? Which has the higher temperature, the wood or the metal? Try it again. Same. Yay, the same. But if you just feel it, you'd say what? Oh, the metal's colder. Is the metal colder? It feels colder because it's a better conductor. Your body temperature is higher than the temperature of everything else in this room. And temperature is higher of your hand than that which you touch. Gang, there's a heat flow, an energy flow that we call heat. Goes from high temperature to low. And when you did that, when you touched the wood, there's a heat difference, but the conductivity not so much. How much energy flowed from your hand when you touched the wood? A lot or a little? Little. How much flowed from your hand when you touched the metal? A lot or a little? A lot. The other L, right? A lot. And it has to do with the conductivity. Kind of makes sense, that stuff, doesn't it? Conductivity. Kind of neat stuff. Hey, I'll show you something kind of nice with that. Here's a piece of iron. Good conductor? Yeah. Here's a piece of wood. Good conductor? Nope. Turns out wood is a very, very poor conductor, as we've talked about. I'm going to put a piece of paper around this iron. I'm going to light up my torch again. Paper doesn't light on fire, gang. Let the paper stick out like this, and it's flaming. Put it against the iron, goes out. Gets charred. That part lit up. Whoops, call the fire marshal. So what's going on here, gang? Well, let's try it with wood. Let's try it with wood. Our test. Be checking the neighbor and see if the neighbor knows why that paper didn't light. You ever read the book by Ray Bradbury called Fahrenheit 451? Yep. That 451 is what? That's the temperature in Fahrenheit degrees at which paper burns. That was about a book burning book, eh? Yeah. Okay, watch this guy. Fire City, that thing's burning up. Look at that. All right? Okay. Why with the wood, but not with the metal? Neighbor time, neighbor time. Okay, what'd be the answer, gang? Most of the energy here went to what? The paper or the metal? The metal. How much was left in the paper? And before I can get the paper up to 451, I've got to make that very, very good conductor back there 451 too. And that takes a lot of energy to do. And so you didn't see the paper ignite. It never got to 451. This is considerably more than 451 degrees, considerably more. When I wrapped it around the wood, look, the wood's all scarred now. Look at that. You saw the paper light up. Why? Because I didn't have to heat up all the wood to 451, just the surface. See, just the surface. And it right up easily. But on a piece of metal, all the heat's conducted all through here. Let's try something similar. This time, I've got, I'll take a paper cup first. Paper cup, some water. Okay, my flame again. There we go. Water in the cup. See, no fire at all, no flames at all, gang. Except the edge. Okay? But I could just about bring that to a boil. And yet if I take a cup like this, okay? Any fire marshals around? Okay? You kind of get the idea. Ain't that nice? And this over here, it turns out just the edge you see there, the edge that's not in touch with the water. But the same type thing is happening here. Not so much because of the conductivity of the water. Water turns out to be not a good conductor. But something else is going on here, gang. And what is it? Oh, I can read your minds. I can read your minds. You're all saying, but gang, you're taking a fluid which has an enormous specific heat, Hewitt. And if you want to increase the temperature of that, honey, you got to put a lot of calories. And you got hardly any left over for the water. I mean, for the what's the outside made of? Begin with a P? Paper. Okay. So it turns out, yeah, most of my energy is being absorbed by the water, and it's a little bit warmer, but not very much. I'll show you something really neat. I'm going to put an ice cube at the bottom of this. Whoops, I hope I can get an ice cube in there. Oh, get in there, son of a gun. Uh-oh. Okay, see the hunk of ice down there, gang? And I'm going to wedge that ice in there with this paper clip, because I'm going to pour some water in there, and I don't want the ice to float. I got the ice wedged down there. Now I'm going to fill it up with some water. Okay, that was the cup that I didn't have the water in, yeah? Okay. Now what I'm going to do is I'm going to get this going again, and oh, wait. I'm going to bring the top to a boil, and the ice cube at the bottom is still intact. Look at that, gang. Water's boiling. But down below, can you see the piece of ice? The ice is still in there. Ain't that right, gang? You see that? So that shows that water is a pretty poor conductor. Remember we talked last time about the idea of the 4-degree water at the bottom of the lake? And the summertime comes, why doesn't that whole lake all heat right up? It turns out that that water will not conduct the energy of that sunlight down very far at all. Water is not a good conductor of heat. It's a poor conductor. And you saw that here. I boiled the top, and that heat did not conduct downward to melt the ice. Interesting, interesting, interesting. This world we live in, yeah? It turns out that air is a good conductor or poor conductor. It turns out it's a poor conductor. And aren't you glad? Because what if air were a very, very good conductor? How would you feel all the time? Begins with a C, ends with O. Put it together, gang. You would feel cold. Let's suppose the air were as good conducting as like a piece of metal. Do you ever stand on the nut at home and lean up against a metal door? Whew, it's cold to the touch. But that metal door has the same temperature as the air around you. So be glad that air is a poor conductor and a good insulator. In fact, when you want to keep yourself warm when you're going to go camp and that sort of thing, don't you get a down-filled sleeping bag? What's all the down for? It's holding air in one place. It keeps the air from circulating. And that down will just hold the... How about animals? You wonder about the animals. How do they make it up in the snow-covered mountains? They're covered with fur. And that fur puffs up, and guess what it holds inside? Begins with A, ends with R. Air. And that air is a very, very good insulator. So most of the things that keep you very, very warm in a cold climate, like that which insulates, like styrofoam, yeah? Or spun glass, or things like that. They're all what? They're things that hold air. See these the thermal underwear they have now? The thermal underwear, you look at the thermal underwear and all this is like a net, like a fish net, and you put that on and that's going to keep you warm? But over that fishnet underwear, you put a regular t-shirt. And now what's trapped between your skin and that t-shirt? Begins with an A. All right, ends with R. Air, okay? And can that air circulate? No. If the air warmed up and just went away, then you get cold again, see? But it's all held there by the little netting. That's what it is. When that stuff first came out, I looked at that and said, what? Because, you know, this is going to keep you warm, honey. And they show you something with all these holes. Say, all these holes? That doesn't sound right. But wait a minute. I know what that is. It begins with a P. It begins with an F. What is it? Physics. Oh, you don't be knowing. Physics. Okay. Yeah. Oh. Let's talk about convection. Convection, the other form of heat transfer. First conduction, then convection. Convection's what, gang? Convection is the moving of fluids. For example, if you heat part of your bathtub up, pretty soon this part is hot too. A little conduction going on there, but mostly the water is kind of moving around in currents. And so when you carry heat from one place to another by virtue of currents in a fluid, we just have a name for that, convection, and it has a lot to do with the climates of the world. Isn't that true? Convection. So we get convection currents. You hear that term a lot. It turns out that warm air, when warm air rises, something happens to the warm air when it rises. Do you guys know why that warm air does rise, by the way? If you're painting the ceiling, and you're way at the top painting, you'll find out it's a lot warmer at the top of that ladder than if you're laying tile on the floor. And someone says, how come it's so warm up there? Oh, it's warm up there because warm air rises. Somebody say to you, well, how come warm air rises? You say, well, it's warm air is less dense than the other air, so it rises. Well, someone says, how come it's less dense, it rises? Well, because it's less dense. Well, come on. Why does less dense air go up? Well, there's probably no reason for that. It's just a rule, man. It's a rule, okay? Why does less dense air rise, gang? Do you know why and why? If a bag of air goes up, and then take air and put it in a great big plastic baggie. Now, can you see it? Where's the greater air pressure, on the bottom of that baggie or on the top? On the bottom. And if that air is expanded, what happens to its density? Less dense. So a greater density air from below will push on that pocket of air harder than the air above, and it will be buoyed right to go up, 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 up. But you know, we can understand this from another point of view, and that's thinking small. And let's think small. You got one molecule, and let's suppose that molecule is hot and stays hot. To say that one molecule is hot is to say it's moving around faster than the molecules around it. Now here's a thought experiment. If you have a molecule that moves faster than all the others, and you let it go here, bap, 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 and it's going to hit all these other atoms, right? It's going to hit. Why would it start to migrate upward? You know it would. Before you know it, keep going up, 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 and all these hits, it keeps going up, up, up. It doesn't go down, it only goes up. It doesn't only go up, but on the average, it goes up. Can you be thinking of a reason why? Check your neighbor. See if your neighbor can be thinking of a reason why. Okay, gang, let's look at this, thinking small. Why is it that one molecule moving faster than any other? And by the way, a helium atom will do that. If you take a helium atom and let it go in this room, it'll continually go faster than any other molecule. Does anyone know why? Why would helium molecules move faster? You guys know any helium in the atmosphere finds its way at the top? It's going faster. Helium is the fastest moving molecule of any group of molecules around. In fact, helium stays in the atom form, just one atom. Doesn't gang up into molecules. And a helium atom is very fast. Let's suppose we have some helium gas in the room here. Would that have the same temperature as the air in the room? Suppose I have a helium balloon here, and it's in contact with the air in the room. Won't it come to the same temperature? Yes, it will. The air in this room all has the same temperature. That doesn't mean every molecule is going exactly as fast as the other. It means on the average they are. The average kinetic energy per molecule is the same for everything that has the same temperature. So helium atoms move faster on the average than others because they are smaller. Let's use the equation to guide our thinking. Remember we talked about kinetic energy before, gang? Let's get into a little physics here. Now this is a little deep physics. That's the expression for kinetic energy. That is also proportional to temperature. To say two volumes of gas have the same temperature is to say those two volumes of gas have the same kinetic energy per their molecules. So the kinetic energy is the same. Now a helium atom has a very, very tiny mass. And compared to the other masses like the oxygen and nitrogen, they have large masses. So I could put the oxygen and nitrogen like that. And if that has the same energy as the helium, but the helium has only a little mass. So what must be the end of the story, gang? Check your neighbor. What's got to happen? If this is going to be the same as this, what's the V going to be? So little things that have the same kinetic energy as big things must necessarily be going faster. I can put it to you this way. Let's suppose there's a mouse and an elephant running down the street. And I tell you that the mouse and the elephant have the same kinetic energy. Now, to say they have the same kinetic energy is to say that when they hit the barn door, they'll do the same work, the same damage. From the fact that an elephant and a mouse, honey, running down going to do the same damage when they hit the barn door, is that enough information for you to say which is going faster and which one's going faster? Now, that mouse is a bullet. Okay, it'll have to be like a bullet to do the same damage. So it turns out little things will go faster than big things if they have the same energy. That tells you a lot, gang. That tells you why there's no helium. Why you don't get helium. All the helium atoms are going so fast, they're going at escape speed. They escape the Earth. And what helium there is at the very, very top, it's all gone. It goes out. The helium you get in your balloons, that comes from under the ground. When they're mining gas, they get helium in there too. Later on, we're going to learn about where that helium comes from. It comes from the radioactive decay of elements like uranium and radium. That's what it is. That's the alpha particles. So next time you see a kid walking down the street with a helium-filled balloon, say, hey, radioactive decay waste. True or false? Hands out true. That's right. That's what it is. They're alpha particles. Slow down. Yeah?
Yeah, really?
Yeah, really. Yeah. It turns out when that warm air rises, and it rises, by the way, because I didn't mention that, it rises because in its migrations, every time it happens to be going down, does it see a lot of atoms or a little bit? A lot to bounce off. When it happens to be going up, does it see a lot or a little? Not quite so many as down. So when it's bang, 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 won't it finally bumble to the regions of less pressure? And it can go a little further with every little bounce, and it comes back down, there's more underneath. So when it's zillions and zillions of bounces per second, it'll find its way right to the top. Just like if you had a whole lot of people in a room, and they're all dancing around or something, and they're all crowded to one end of the room, and you put some drunk in the middle who moves faster than anyone else, and that drunk is out of it, and you want to go find that drunk later on, you look in the part of the room where there's very, very few people. That drunk will just bumble right to the region of less opposition. Very, very improbable that he'd bumble to where it's all crowded. Because every time he'd bump into a person, he'd go further this way. And he'd keep bounding back. Same with a molecule in the room. Finally find itself at the top, if it's faster moving than the others. See, but air doesn't do that, because air cools off. When you light smoke, you light a fire, you see the smoke go up, yeah? But the smoke doesn't keep going forever. What's the smoke finally do? It finally settles off. And what's going on there? The smoke molecules have lost their energy. They've bumped into the other things, and all those bumping, they kind of slow down. And when they're going no faster than the other air, they'll just take on with that air, see? But helium will never slow down as slow as the other atoms because it's got the same energy, it's got more speed. Does that make sense? You got some physics today, huh? So that's why helium is up in the... huh? Okay. That's not, by the way, why a helium-filled balloon goes up. The helium-filled balloon, it's all trapped. The helium-filled balloon goes up for a different reason. Because there's more pressure on the bottom than the top. And the buoyancy is bigger than the weight because it's very, very low density. See? That's a different idea. See? We're talking about now one little atom. It doesn't make any sense to say one little atom being buoyed. Okay? It does get hit more from the below than above. But so doesn't every other kind of atom. But this kind of atom is moving so fast, it migrates more than others and finds itself out there very, very quickly. I want to show you guys something really dramatic. Do you ever wonder when you take your friends, you go to the mountaintops, and up there the temperature is what? Cold. It's cold. Now the mountaintops are closer to the sun. So your friend says, gee, I see we're closer to the sun. We should be a little warmer. And the higher you climb, the colder it gets. Did you ever wonder why? Is there anyone here that ever went up in the mountains and it got cold and didn't wonder why? I want to see what you look like. Stand up. Everybody wondered why? Non-science types do? Yeah, we wonder how come it's cold up there, okay? And why is that? It's because when that rising air goes up, what does it do when it gets to regions of less and less pressure? Cools. But why does it cool? Begin with an X. Expands. It expands. Just like a helium-filled balloon would expand, wouldn't it? And so when the air expands, then the air cools. HC. I got a demonstration for you all to try right there at your seats. Are you ready? Everyone have a hand? Put your hand in front of your mouth, and with your mouth open, so when you breathe, so the air doesn't expand, I want you to blow. Little disruption there, okay? Okay. Now bring your mouth down really tight so the air expands when it comes out. Notice any difference in temperature? Try it again, gang. Open mouth. Open mouth. Now closed mouth. So the air expands. Okay, you want to see that more dramatically? Watch this. Here's some steam here, huh? Would I dare to take this glove away? Yeah, easy. Easy city, man. No problem. Hot or cold? Begin with a C. It's cool. Relatively cool. HC. I'm not going to put it way down at the nozzle. It turns out that that which you are seeing here, gang, is not steam. That which you can't see, that's the steam. But what does that steam do? Begin with the X. Expand. And when it expands, what's it do? Begin with another C. Cool. And there's your evidence of it right there. Isn't that remarkable? So try this at home, huh? It's cool to the touch. And that gets hotter, 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 hotter. But up here, it's relatively cool. Cooler here than out here. I wonder if there's a reason for that. How many say, well, no, there's probably no reason for that. It's just one of those little flukes of nature. And that's what we're going to be talking about. What was the reason when you blew like that it was hot, and you went like that it was cool? And did you notice it was appreciably cooler doing that? That's because the air had to expand. Now, we can understand that if we think small. Here's a molecule moving around. It's going to hit its neighbors, right? Sometimes it's going to hit a neighbor and bound off with more energy. Sometimes it's going to hit a neighbor and bound off with less energy. Now, when does it gain and when does it lose? Look at this ping pong paddle I have here. See it? Watch this ping pong ball come in and hit the paddle. Watch this. Watch this. See it went off at the same speed? It's because I held this very rigidly. Watch again. Kinetic energy in, kinetic energy out. Same. Did you see that? This time I'm going to move the paddle up like this. Now watch. Did you see it move away faster? Why? Because I hit it. I belted it, honey. I come in, boom, and I gave it energy. When you got a pump and you're pumping up air, you ever reach down and touch that pump? That pump is what? It's hot. Why? Because you've belted those molecules. What do you have when you take a baseball bat and start hitting balls? What are they going to do? Slow down? They're going to speed up. And so what happens? That paddle comes in, boom. Now, what happens in air when an air molecule is moving by and it hits and it sees another one that's coming toward it? Boom! It could bounce off with more energy than it started with. This one slow down, but that can happen. As we see with a paddle coming in, boom, goes off faster than it came in. How about the converse? Let's suppose my paddle's going away, and now my ball hits. See that? Should I do it again? Okay, it dribbles down. It loses speed. So if molecules will hit others that are going away, will they rebound with greater speeds or lesser speeds, or is this not clear?
Lesser speeds.
Can you see it's lesser speeds? Lesser speeds, gang. Okay? So what happens when air expands? Go right down in there in the microscopic realm right there and take a look. What do you see? Hey, man, where are all you guys going? They're all going away, yeah? And you're a molecule right in there. Now you're going to bound off all those guys. And when you bound off, do you pick up speed or lose speed? You lose speed. That speed goes out to here. All that energy spreads out. In there, you got less energy. You put a thermometer, you felt it right here. It's really cooler. It's cooler when it expands. Does that have a lot to do with weather or not? A lot to do with weather conditions. Expanding air will chill, will become colder. Neato? Can you see why? Pretty neat, huh? Yeah. So you're at the top of the mountains, honey. You know why it's so cold up there? That air has been expanding. And when it's been expanding, of course it's cold up there. Oh, closer to the sun. No, that expansion rate, that expanding of that air cools it a lot.
So actually when you heat something, it expands and you're having to put more energy into it because to compensate for it expanding too, to heat it up.
Oh, now we can get a little mixed up here. It turns out that when you heat some air, like you heat anything, you will make it grow. You will make it expand. Okay? So you can force something to expand. I can take a balloon of air and hold it over a stove, and it will expand. Okay? We're not talking about that. It doesn't follow now that expanding, see?
Not contained.
Well, to say that you can heat something up and make it expand is one thing. But now we're saying if the air will expand by itself, push outward, when it expands, what happens to the temperature in the middle of that? And that drops.
So the reason for expanding is because it was going from a region of higher pressure to lower pressure.
Excellent, excellent, excellent. The reason it expands is because the air goes from a region of high pressure down here, deep, deep down in the bottom of this ocean of air. And when it rises, what's it going to do? Like the balloon, like the fish, like the scuba diver, we've all talked about. These ideas are all connected, gang, huh? And as it goes up, 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 it's going to expand. And we learned a new thing today. As it expands, son of a gun, it cools. Why does it cool? Because the molecules in the middle are making impact with things on the average that are going away. And so they rebound with less speeds. And the effect is big. I mean, it's quite noticeable. There's a third form of heat transfer again. And the third form, not conduction, not convection, but what? Radiation. That's right, radiation. And heat radiates from the sun. It gets to us by the process of radiation. We're going to talk about that a lot later on when we talk about electromagnetic theory and we talk about light. But I want to talk about one aspect of that now. And that one aspect is that the frequency of that radiation is directly proportional to the temperature of the source. Why I want you to know about that is because I want you to know a little bit about what people are talking about when they talk about the greenhouse effect. You've all heard about it. The fact that there's a layer of carbon dioxide in the world now that is holding in the heat, and the Earth is becoming warmer and warmer as the years go by. At least that's the idea. I want you to understand that. And to understand that, we have to consider a formula. And the formula makes sense, kind of. It just says that the frequency of radiation is directly proportional to the temperature of the source. Let me give you an idea. You see this rubber tube I have stretched out and connected to the wall over there? Can you all guys see the rubber tube? What color is the rubber tube?
Hello.
Can you guys all be looking at the same rubber tube? What color is the rubber tube?
Green.
Well, take your pick, all right? Put on your glasses. But we got a rubber, it looks red to me. There's a red rubber tube. You guys see the red rubber tube? Now I'm going to shake the tube. Bloop, 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 bloop. What do you guys be seeing across the room? Waves. Isn't that right? Can you see the waves? Now I want you to look at what happens to the frequency of the waves when I shake it faster. How many see the wave shaking up? How about when I shake it like this? Bloom, bloom, bloom. What's the frequency of the waves? Bloom, bloom, bloom. It turns out that the faster I shake, the higher the frequency of the waves. Is that far out or not? That's not far out at all. That's common sense. If you shake the thing like this, plump, 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 you get long, lazy waves. If I shake like this, bloop, 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 I'll get little short waves like that. We'll learn about that later, okay? That wavelength, frequency. Turns out, well, I won't even talk about wavelength at this point. Let me just talk about frequency. That sun, high temperature or low temperature? High. The Earth, relatively, high or low? Low. Now it turns out that everything is emitting waves. You and me and everything else that has a temperature above absolute zero. Everything's emitting waves and everything's absorbing waves. We're just going to concentrate on the sun and the Earth for now because we're running out of time. The frequency of waves emitted by the sun are very, very high. The sun's temperature is like this. So the frequency of waves is like that. So high, millions of billions of cycles per second. And we call that light. And light carries energy, electromagnetic energy. High, high frequency. Why is it high frequency? So high it's called light? Because the temperature of the sun is very, very hot. Okay? Now that light comes down and hits the Earth. And so the Earth warms up. But the Earth re-radiates that energy back out. But what frequency? High or low?
Low.
Low. Why low? Because the temperature of the Earth is like this. And so the frequency of radiation that's emitted is like that. That's way down below the threshold of the red in the color spectrum. We call it below red. In the physics class, you'd never say below red. In the physics class, you'd say what, gang? Infrared. So it turns out the sun emits visible light, high frequency, and the Earth emits infrared, low frequency. Now it turns out different things, different materials are transparent to different wave bands or frequency bands. It turns out the atmosphere of the Earth is transparent very, very nicely to visible light. Of course it is. You can look up and see the sun and the stars right through it. We have a transparent atmosphere for light, high frequencies. It turns out the atmosphere, especially if it has a little water vapor in it, is terrible. Is a terrible, well, not terrible, but it's a much less transparent material and medium. So what happens to us, gang, is this. Here's the sun up here. And the sun is emitting very, very high frequency rays. They come right through the atmosphere. And the Earth radiates low frequency, and they can't get through the atmosphere. A lot of them can, of course, but a lot can't. And those that can't, then, this energy starts to pile up in here. This happens in your car. You leave your car out in the parking lot, gang, okay? Why is it when your car out in the sunlight is so hot when you open the door? Well, you can say, well, it says heat, it's been heated in the sun. But look a little carefully. That sunlight is coming right through that window. High frequency, right through the window pane. And what it does, it hits the inside of your car and heats it up. And the inside of your car re-radiates. Now, if the inside reflected, you'd be okay. That's why you put that silver stuff on your windshield. That's going to reflect the light. And that reflected light, turns out reflected light doesn't change its frequency. We'll learn later on, if you're wearing a blue shirt and you stand in front of a mirror, guess what color your image is, gang? Son of a gun, blue. Now you put on a red shirt and you stand in front of a mirror, what is it? Whew, same shade of red, okay? It turns out that reflection doesn't change frequency, but re-radiation does. Because if you catch it, re-radiate from one source, and re-radiate from the other source, you get a different frequency. And that's what's happening with the greenhouse effect. It re-radiates a frequency that can't get through, especially that carbon dioxide. And that's holding the energy in. You kind of be seeing that? Important stuff. Okay, more physics next time. Yay.